Okay, here we go. So for the past 4 weeks, we've been talking about a bunch of different equations. To summarize all of them and to unify all of them into one big picture to help us memorize, we have this diagram here. We first start out with the first tool called the electric force. The force between two charged objects, Q1 and Q2. And if they're separated by some distance r, following this formula where kq1, q2 over r squared, that would give you the force between those two charges. And that units are going to be in newtons. And then we move over and we go to the electric field. And this one, I was stressing the fact that it is the electric force per charge. Hence, if you look at the units, it's newtons per coulomb, because I'm dividing out one charge. It's saying, what would the force be had you put a charge there, however many charges you do put at a certain point, a distance r away. So that's the electric field. And now we move to the two new concepts that are very closely related. Electric potential energy. Let me stress, this is energy, whereas this one's just called electric potential. And to not confuse things, people usually just call it voltage. Now, when you look at this diagram, you can see that they're very similar and there's a relationship between each one, right? To go from the left side of this diagram to the right side of the diagram, I'm dividing by Q, right? And to go from top to bottom, what would I do? What do you notice? There's a negative, right? And there's also only one r. So you integrate. So go from top to bottom. The integral of 1 over r squared is negative 1 over r. See that? Saying the opposite, the derivative of the electric potential energy would give you back the electric force. You see that? So there, that's a nice way of understanding how to go between each one. Now, how can we understand the concept of each of these? Well, I'm going to demonstrate it by talking about this, the voltage. There's two ways you can say what voltage is. Watch. First one is, it is the electric potential energy per charge. Or you could say, it is the electric field over a distance. You see how I got those two ways of saying that? So those are the wording, those are the key phrases in the test question or something. They'll say, what is the electric field over a distance? Then, they're talking about voltage. Or what is the electric potential energy per charge? Oh, they're talking about voltage still. Two ways of saying the same thing. You see how I did that? Just by looking at the units. And we also had this weird thing, this offshoot, the electric flux, right? The electric flux was charge enclosed around some boundary that we draw, and then we take all the charges in there within that boundary. That's going to be the electric flux. And we could also define it by saying that it is E dot A, where A is the normal to the surface vector, and the dot product between that and the electric field. That is the electric flux. And if you look at its units, you can always figure out its units, right? Because if it's E dot A, electric field times area, then I already know the electric field units. It's newtons per coulomb times area times meters squared. So what's another way I could say this? You could say that it is the electric potential, or it's the voltage over a distance. You see, it's voltage times meters. That's electric flux, if you think of it like that. So you see how there's different ways of saying that by looking at the units. So there we go, we have that. We also have the analog, right? You guys have seen the gravitational equation, right? So I'm going to make some adjustments. So draw a new grid in your notebooks and replace this. So now it's not electric anymore. Let's replace everything with, let's cross that out, let's call that gravity. Gravitational force. It's just G, M1, M2. Right? Write that then you have first quadrant. What's this one here? Well, let's replace that. So this is not, this is, gravitational now. And it's going to be G, M1, M2. And then let's move over here. Let's cross this one out. Although we'll draw a new thing on your paper. So this is going to be, let's call this a new letter, G. Because we're going to have, let's call this G, N. Right? And this would be GM. There we go. Is that right? And one more. Now the units are a little different. Now it's going to be over kilograms. Because we're talking about masses. Right? Okay. Anyone spot a mistake here? Nah. Okay, that's right, right? So if you have the gravitational force, it's this. Gravitational field will be this. Gravitational potential energy. And we remember from kinetic equations that it's mgh, right? And let me show you why that is. Because if you take this portion, go ahead and draw a dotted line to highlight that portion. If you take m1 to be the mass of the Earth, r to be the radius of the Earth, and having that gravitational constant big G, this is going to equal approximately 9.81 meters per second squared. Hence, you have mg, right? Otherwise known as little g, and h, because we have mg, h is a distance. So if I'm taking mg times, if I take the gravitational force times some distance, distance cancels out. That's why gravitational potential energy is mgh. So, but it all relates. See, now you can see how it all connects, and from there we're going to start our first problem. Okay, so now that you have this down, write that down. I guess you could probably even say gravitational flux if you'd like as well. So that's the classical picture. Now, we're not really going to talk about the gravitational potential or the gravitational voltage. That's kind of weird, right? Because we usually don't have a storage of mass, right? Whereas electricity, you can store charge, but you can't store mass. There's no mass battery, right? So, unless you can make like a black hole, that would be like a mass battery. So that's a lot of gravitational potential, a lot of gravitational voltage, you could say. All right, so let's stop there. All right, so we have a coordinate axis that I drew. There are 2 points. Point A is located at -0.2, comma, -0.3. Point B is located at 0.4, comma, 0.5. X and Y, right? Now, we also have an electric field that is 325 volts per meter everywhere. So imagine I drew blue arrows everywhere on the board. It's all covered with blue arrows pointing down electric field. We're gonna ask the question, what is the voltage difference between A and B points? So the question is this. What is VB minus VA? Otherwise known as the change in voltage between the 2 points. That's the question. So, because we're asking the voltage, we're going to start with the voltage equation. Start with this. So, remember that dimensional analysis? We were saying that, well, voltage is Newton meter per Coulomb. So if I took the electric field, which is newtons over Coulomb, multiplied by a distance, meters, you get the correct units. So this is where this one comes from. Negative E dot ds is the voltage for one piece, but you're going to have to add up or integrate all the pieces, A, B, like that, like so. But looking at this, we could find that direction ds. That's going to be what is the ds? Well, it's going to point like this, right? And then the electric field points straight down, right? So if I were to find the cosine of the angle between these, find that, that would be E times, ds cos theta. But that would be a little more complicated, and you could get the same answer because you're integrating along the path ds. You're integrating along that path, that diagonal path. However, it's the same thing if you were to integrate along the y first and then along the x. See? So integrate up and over. So we're going to arbitrarily, not arbitrarily, but we're going to conveniently make a point C that's, a right triangle. So that you create a right triangle. So that we can rewrite this by saying the voltage from A to B is from point A to C, and then it's from C to B. See that? So I have this. So now the limits of integration, I want to go through this. So for the limits of integration, since I'm integrating along dy, I'm going to look at the y coordinates. So the y coordinate is negative 0.3 to the y coordinate, because that's for my c, right? So that's going to be negative 0.3 and 0.5. And then from this one, for the x coordinate would be, the x coordinates would be negative 0.2 to 0.4. See? So then this statement is equivalent to the one before. We just broke it up to x and y. Then when we integrate this, because we know that E is a constant, right? Because we said it was 325. So we can factor that out of the integration. So if you do the integration, skipping steps here, when you do the calculus, you do the integration, what's the integral of dy? Just y, right? What's the integral of dx? Just x, right? And if you do that, and you do this appropriate subtractions, right? Then you're going to get 0.8 meters, which gives you a total voltage of plus 260 volts. There you go. So you copy that down, check yourself, do a little practice integration so then you can see if you're doing it right. Alright, so that's the first micro problem. Alright, and let's stop it there. Any questions? Okay, we have a square and we have two charges. One is Q, one is 2Q. And we have 2 points, A and B, on a square. The square has side lengths of D. So we know the hypotenuse is D root 2 because of our isosceles 45, 45, 90 triangle. Right? We're going to start out with the voltage. We're going to use this as an outline, right? Voltage equals negative KQ over R. R being the distance between the charge and the point of interest. Right? These are the questions. What's the voltage A? What's the voltage at B? What's the difference in the voltage? Potential difference. That's another way of saying it. That's the lingo. All right, so if I look at the voltage at point A, it's going to be a sum of two parts. One being the Q, one being the 2Q. So let's put in the Q, and this is plus 2Q. Oh, that's just like right, 2Q. So it's Q and the 2Q. What are the corresponding distances? Well, for this one, A is a distance D away. See? It's a distance D away from the Q charge. Point A is what distance from 2Q? It's D root 2. Right? Awesome. So there we go. That's the answer for the voltage at A. B, it's going to be, well, again, the sum of Q, the Q1 and the 2Q1, but we've got to look at the corresponding distances. So B here we have D root 2. And then here we have, well, this time the 2Q charge is going to be a distance D away. So let's do a quick poll. They look very similar. Yes, the denominators are different. Which one's going to be the higher one? And which one's going to be the lower one? Show of hands for a vote. Is the voltage at A going to be higher than voltage at B? Yes, no, maybe so. Who votes by show of hand, that the voltage at A is higher than voltage at B? No, what about, so the other question, who votes that the voltage at B is larger than voltage at A? So these guys here, everyone's here saying yes. Consensus has dictated our free pressure, right? So we have, yes. What this ends up being is 5.43 kilovolts, and this one's going to be 6.08 kilovolts. The voltage at B is going to be larger. Let's understand why. Well, the 2Q is closer to B. Two charges are closer to B, whereas those same two charges are farther from A. That's the logic. So, that's why the voltage at B is going to be larger. This is a real nice classic question on the exam, let's say, that they give you a situation like this, and they ask you to quickly analyze which voltage is higher, B or A. They're both the same, or none of the above. Right? That's the cases. So this is a nice way you can analyze that real quick. All right. So yeah, that's the second one. Okay. All right. Now we have this situation, guys. We're going to revisit that charged rod that we did 2 weeks ago. However, this charged rod is not uniformly distributed. It is in fact, it is in fact like changing with distance, varying with distance. So I call this the linear charge density varying with distance. Let's try and see if we can understand this. The charge density, the charge per distance, is equal to some constant alpha times the distance, whatever the distance is. Well, that tells me that if I'm at the origin, then x is 0, so lambda is 0. As I keep going, when I'm at a distance of 1, lambda is alpha times 1. When I'm at a distance of 2 from the origin, then lambda is 2 alpha. You see, so the linear charge density is increasing as a function of its own distance along the rod. So that's why at the end here, the gradient, I would draw the blue dashed lines representing the amount of charge. So it's a lot, charged a lot here, but it's not when you go back to the origin. Okay? And the question is asking, what are the units of alpha? So this tells us to look at that conceptual framework. Let's look back at the units. Well, lambda. Well, lambda, like we said, was, looking at its units, it's charge, coulombs, per distance. Like that, right? So, if I do this, if I set this equal to alpha x, well, we know this x here is a distance, meters. So I just divide that underneath. See, if I make everything, you can see that if I took x, which this is going to be meters, I would have to divide that to solve for alpha, to look at its units. So its alpha's units are going to be coulombs per meter squared. Pretty straightforward, right? That's the units of alpha. Okay, now, how do we find the voltage at A? At A. So, let's write this down. Well, let's start with the structure. This. We're going to start with this structure, and a piece of it is going to be dV. A piece of it, like a piece of the voltage, contributing right here. So if you look at the situation, there's almost no charge here, but there's some charge just a little bit over. And this distance, let's call that distance x. So combining that together, at any arbitrary distance from that origin, that is the distance r, which equals d plus x. That's how you can see the relation. So from any point on this charged rod, the distance it is to A is d plus x. So x is varying, r is varying, whereas d is the constant. All right, so now we have that. We can look at our structure here. So we want to, well, this is going to be minus k dq over r. Now I can take that r, plug it in here. Almost done. Negative k dq over d plus x. We are integrating along the charged rod. So that's along the x-axis. What's the problem? We have a dq. We have to relate dq to dx. If I integrate both sides, I'm going to get back the voltage, right? Yeah, we get voltage equals negative k integral from 0 to L. K, I'm going to leave a space here. D plus x. I'm missing something? Oh, I'm sorry, bro. 2 Ks. I'm sorry, 2 Ks. My bad. Thank you. Thank you. All right, so from there, well, let's go back to what lambda was, right? We just said here, lambda. Let's look at lambda. Lambda, we know, is alpha x. Lambda, we know, is the amount of charge per total length. That charge density, charge per length. So this is also correct because it's going to be in proportion to the right little cube. dx. See that? This is the proportion idea. Now, lambda is alpha x. So alpha x equals dq dx. Multiplied by dx over here. So alpha x dx equals dq. I guess I should have used a capital Q. That doesn't really matter. But now I can plug in, right? My dq, I have that piece. Let's plug that in. So it's going to be alpha x dx. That's the answer. That's going to be the voltage at A. Yeah. Now, that's going to be some sort of U substitution, and I'm just going to write the answer. After you do the calculus of integrating this, V of A is going to be, where is it? Good answer. Ah, there it is. I'll try each. V of A equals K alpha L minus, sorry, I'm not getting a small room here, natural log of 1 plus L over D. Is that too small? I'm going to read it out. Voltage, the answer is going to be K alpha times the quantity of L minus D times natural log of 1 plus L over D. So this is write that down so you can check your integration. Check your practice this integration. Check it and see if you got that right. Now I'm going to, now that answers this question and this question. But now we ask, what's the voltage at B? I'm not going to go through this one because this one is really complicated. But I just wanted to show the setup. How to set it up. Because sometimes the questions on the exam is just, what is the setup? But not integrate. Don't integrate it. But what is the setup? So, this is still okay. Now we don't really care about this part. And we don't need to know that anymore. Delete that part. There. Alright, so that's that answer right there. Okay. We're going to have voltage at B is going to equal, well, negative K. It's still going to be negative K. And the top part it's still going to be this distance. If this is L over 2, L over 2 minus x would give you some amount, and this, let's call this distance here h. Right? If we call that h, you see that r, tell me if this makes sense here, if you guys can recognize this. It's going to be h squared plus L over 2 minus x, that quantity squared. What is that formula? Right, where did I get that from? Just pull out from my butt. Right? It's just, what is it? This is just the Pythagorean theorem, right? See? H squared plus this distance, defining this distance squared. And the square root of that, that's r. So you just plug that guy in here. So you have square root h squared plus L over 2, the quantity. Right? Boom. So that's the setup. That's a very common question, how to set up the equation. Because the answer for this is really complicated. When you integrate that, you get this crazy thing, which I'll just write for your, so if you want to check it, so it'll be negative k some room. Do this. Plus. There you go. If you integrate this, you'll get this craziness, this crazy business. So if you want to practice that, that's also great. So copy that down so you can have a check to check yourself if you're integrating correctly. It looks like you do some substitution and move things around, the new variable. And then plug it back in after you integrate. Alright, so this is a good calculus practice. Alright? I'll leave this up. Alright, here we have an example problem. Very similar to the one in the packet, so pay attention to this one. We have a charge conducting sphere. It says that the voltage immediately outside it, I'm going to label at point A, is 200 volts. 10 centimeters farther from the center of the sphere. The center, farther from the center of the sphere. So this must translate to 10 centimeters. That the voltage is 150. And now our task is to find, well, what is that radius of that sphere? So what we could do is we could start with our equation. We know that. Oops. V equals KQ over R. Oh, negative. All right. That's our structure. That's where we're going to plug in. So let's write this. VA equals negative KQ over, let's do capital R, right? That's the VA one. What's the VB one? VB equals negative KQ over R plus 10. Right? It must be, there's 10 more than the R. Now, I conveniently know these two numbers. And with two numbers, you can multiply them, you can subtract them, you can divide them, you can do whatever you want. Well, I'm going to decide to divide them. I'm going to say, well, VA over VB equals 200 over 150. 200 over 150 is 4/3, right? So, if I take these equations and I take the ratio of these equations, they equal 4/3. See that? That's the link. That must equal 4/3. So let's write that together. Put them together. Minus k cubed over r over minus k cubed over. See that? V of A over V of B must equal 4/3 because we know the answer is. Now, I can cancel what? I can cancel this. The minus k cubes, they cancel. So I gave this opportunity to my last class. I'll give anyone 1 plus 1 on this worksheet today if you can solve for R right now. Yeah, solve for R. Just an algebra problem. Whoever's the first one to raise your hand. Yeah.
I converted back to meters before.
Yeah, it is. Oh, that doesn't. You already got it. Darn. All right, so you get a. But you already did the problem, right? So. Well, no. Next one, the Q. What's Q? Plus 1 for anyone who calculates the Q. What's Q gonna be? Well, you figure out R. You can use another location. You need to plug in things.
2, 3, 4, 5, 6.
What was it?
1.3.
Not 1.3. No. Yeah.
Negative 6.6.
Well, you already answered, but that is correct. But you already answered. Give somebody else a chance. Who else gets it?
If I just overheard them say the same exact thing you said,
Well, you gotta show me how you got it with the,
you just.
What would you do?
You just plug in R.
For which one?
I mean, you can do it with both.
Yeah, for either one, right?
Yeah.
Yeah, that's right. So what was it? What was the answer?
No, it's 6.67 times 10 to the third.
No, not 10 to the third. No, sorry.
What did R equal?
R.
Can I
So
go like
R was 0.3 meters. The question is, what's Q? When we have these numbers, when we plug into yes.
6.67 times 10 to the negative 9.
Yes. Got it. Yeah. All right. That's just a small little thing to get people to do it.